In this lecture, we are going to solve the numericals in series RL transient circuit using classical method. So this is a problem given. In the circuit shown in the figure, initially switch is open for long time. At t is equal to 0, switch K is closed. Obtain the expression for current in the circuit for t greater than 0. Find the value of current at t is equal to 0.25 seconds. So first we have to obtain the expression I of t. And then we have to find out the current value at t is equal to 0.25 second. What will be the current? So next we have to find out what will be the current in the circuit in one time constant period. So here in the case of RL series circuit, time constant is given by L by R. Okay. So now next determine the instant of time at which the current in the circuit reaches to 1.2 ampere. So this is the circuit given RL series transient circuit. R value is 8 ohms, L value 10 Henry and V value is equal to 12 volts. Okay. So now let us assume that at t is equal to 0 minus, that is just before closing the switch. So it is given that at t is equal to 0, switch is closed. So we are assuming that at t is equal to 0 minus, just before closing the switch is kept open. So whenever the switch is kept open, the current flowing through the circuit will be 0. So at the instant t is equal to 0 minus, that is I of 0 minus will be equal to 0. So whereas the inductor will not allow any sudden change in current. So at the instant t is equal to 0 as well as at the instant t is equal to 0 plus, the current value will remain the same, that is 0. So this is assumed as the initial value of current. So here 0 minus is instant just before closing the switch and 0 plus is instant immediately just after closing the switch. Here at t is equal to 0, switch is closed. Okay, this is the initial value of current. Let this be equation number 1. So next, for t greater than or equal to 0 plus, switch is closed. So now we'll draw the equivalent circuit. This is the equivalent circuit. Whenever the switch is closed, the current will start flowing through the circuit. Let us assume that the current is I of t and it is flowing in the clockwise direction. So now we have to apply Kirchhoff's voltage law in the figure 2. Okay. So already we know that in a closed circuit, sum of the voltage rise will be equal to sum of the voltage drops. That is Kirchhoff's voltage law. So here the voltage rise is defined with respect to voltage source only, and that too if the current direction is from negative to positive, then this particular voltage source is defined as a voltage rise, otherwise it is taken as voltage drop only. And then the voltages across the resistor and inductor are defined as a voltage drops. So now voltage drop across the resistor is 8 into I of t plus voltage drop across the inductor is 10 into di of t by dt. That is equal to voltage rise 12. So this is the Kirchhoff's voltage law equation for the equivalent circuit. Okay. So now our aim is to find out I of t value. So now we are going to divide this particular equation by 10 and then rearrange it. Okay. So if we divide this term, so this particular term by 10 and 10 will get cancelled. We will get di of t by dt. Okay. And then if we divide this term by 10, 8 by 10 will be 0.8. So we will get 0.8 into I of t, that is equal to, on the right hand side we have 12. 12 divided by 10 will be equal to 1.2. Okay. So this is equation number 2. So now the equation number 2 is the first order non-homogeneous differential equation of the type di of t by dt plus pi of t is equal to q. So this is the general form of the first order non-homogeneous differential equation. Okay. So let this be equation number 3. Now we can compare these two equations, that is equation number 2 and equation number 3. So on comparison, we will get the value of P and Q. So this is the equation number 2. Okay, this is the equation number 3. So if we compare these two equations, we will get P and Q value. In place of P we have 0.8 and in place of Q we have 1.2 here. Okay. So we can write P is equal to 0.8 and Q is equal to 1.2. So this is equation number 4. So now the solution for this non-homogeneous first order differential equation is given by I of t is equal to e power minus pt integral 0 to t q into e power plus pt into dt plus k dash into e power minus pt. So this is the solution for the first order non-homogeneous differential equation. Okay, so we have to remember this equation. So now we can substitute the value of p and q in order to obtain the expression for I of t. So now I of t can be written as e power minus 0.8t. So we can substitute 4 in 5. So 4 is nothing but p and q value. So in place of p we can substitute 0.8 and in place of q we can substitute 1.2 into e power plus 0.8t dt plus k dash into e power minus 0.8t. Okay. So now here e power minus 0.8t is constant into integral of this particular term. Here again 1.2 is constant, we can take it outside, and integral of e power 0.8t dt is given by e power 0.8t divided by 0.8 over the limit 0 to t plus k dash into e power minus 0.8t. Okay, so now this 0.8 can be taken outside, and so we can write this equation as 1.2 divided by 0.8 into e power minus 0.8t into, here we can substitute the limit, upper limit is t and the lower limit is 0. So e power 0.8t minus e power 0, upper limit minus lower limit plus this term. Okay, so now here e power 0 is 1. Okay, we can substitute 1 here, and then simplifying this we will get 1.5. So the remaining equation is 1.5 into e power minus 0.8t into e power plus 0.8t minus 1 plus k dash into e power minus 0.8t. Okay, so now we can multiply this e power minus 0.8t inside. Okay, so 1.5 into e power minus 0.8t into e power plus 0.8t minus e power minus 0.8t into 1. Okay, plus this term will remain as such. Okay. So now these two, multiplying these two will give you e power minus 0.8t plus 0.8t. Okay, so that will be 0. So e power 0 is 1 here, minus e power minus 0.8t plus k dash into e power minus 0.8t. So this is the required solution. So this is the I of t. So but here k dash is a constant value. Again we have to find out the value of k dash. So now k dash value can be found out by using the initial conditions. So already we have derived the initial condition in equation number 1. So we can substitute the initial condition. So initial condition means current at the instant t is equal to 0. So we can substitute t is equal to 0 in the above equation. Okay. So we will get zero. So in this equation we have to substitute t is equal to 0. So here we will get I of 0 is equal to 1.5 into 1 minus e power minus 0.8 into 0 plus k dash into e power minus 0.8 into 0. Okay. So I of 0 already we know that is equal to 0. So 0 is equal to 1.5 into 1 minus e power minus 0 plus k dash into e power minus 0. So e power minus 0 or e power 0 will be equal to 1. So if we substitute the value over here, so if we substitute 1 here, 1 minus 1 will be 0. Here k dash into 1. So k dash value will be equal to 0. So now we can substitute this k dash value in equation number 6. So equation number 6 is what? I of t is equal to 1.5 into 1 minus e power minus 0.8t plus 0. So this is the required solution. I of t is equal to 1.5 into 1 minus e power minus 0.8t. So this is the expression for the transient response. Okay, I of t. So now we have to find out the value of I of t at t is equal to 0.25 seconds. So we can substitute t is equal to 0.25 in the 8th equation. So I of t is equal to 1.5 into 1 minus e power minus 0.8 into 0.25. So on simplification we will get 0.2719 ampere. Okay. So now in the second subdivision we have to find out the current corresponding to one time constant. So tau is the time constant given by L by R. So L value 10 and R value 8. So 10 by 8 is 1.25 seconds. So if we substitute 1.25 in place of t here, okay, so 1.5 into 1 minus e power minus 0.8 into 1.25 will give you 0.9481 ampere. So this is the current corresponding to one time constant. Okay. So next we have to find out the time instant at which the current is 1.2 ampere. So in place of I of t we have to substitute 1.2 and then we have to find out the value of t. So 1.2 is equal to 1.5 into 1 minus e power minus 0.8 t. Okay, we can take this term down here. So this can be written as 1.2 divided by 1.5 is equal to 1 minus e power minus 0.8 t. Okay. On simplification, we'll get e power minus 0.8 t is equal to 0.2. Taking natural logarithm on both sides, we'll get minus 0.8 t is equal to ln 0.2 or t is equal to 2.011 seconds. Okay, so this is the time corresponding to 1.2 ampere of current.